All right, so continuing on in 6.1, we're going to go back to the how many languages example. You have this written down in your notes. There are the probabilities. I have we calculated the mean, right? For our expected value of 1.457, which means that if you were to select a student at random, you would expect that student to speak approximately 1.457 languages. I've written down the formula for the variance of x, right? And the reason why that's important is because the square root of the variance is equal to our standard deviation. Going ahead and calculating the standard deviation for our number of languages spoken. And then we'll have to interpret that in context as well as soon as we're done. But we still have more here. So we have our probability. So x equals 4 minus the mean times the probability that a person chosen at random speaks 4 languages. And then our next one is 5, which is 5 languages spoken, times the probability that a person chosen at random speaks 5 languages, which is 0.002. All right. Hey, if we crunch these numbers, we get 0.450. Right? The way that we interpret that let's calculate the variance first, my bad. So that is our variance. We're going to have to go ahead and take the square root. Oh, come on. All right, so that means that the standard deviation of x is going to be equal to the square root of our variance, which turns out to be 0.671. So we need to interpret that in context. It's the most important part of it. And in context, you would say that the number of languages spoken by a randomly selected U.S. high school student typically varies by about 0.671 languages from the mean. Just another interpretation of our standard deviation. Cool. So that is discrete random variable distribution, right? So now let's look at continuous random variable distribution. So one example of a continuous distribution would be a normal probability distribution, right? In your book, it says that a continuous random variable x takes on all values in an interval of numbers. The probability distribution of x is described by a density curve. The probability of any event is the area under the density curve and above the values of x that make up the event. So essentially, we've already been doing this, all right? We've already done this by calculating proportions, right? So we had a normal density curve where we had our mean there, right? And we were able to calculate very easily areas to the left of a certain given x value, right? Before, though, we interpreted these as proportions, right? The proportion of people who would say yes or something like that, right? And now we're going to actually calculate them as probabilities. And that's really what that normal density curve, its main purpose is. So, really we're going to be doing a lot of the same work, but we're going to add some different notation. All right, so we have, for example, weights of 3-year-old females. Oh, there's another hyphen. So we have some data about them. They're roughly normal, which means that I could express that distribution in terms of, if you guys remember this. So the problem that I have says, hey, they're roughly normally distributed with a mean of 30.67 pounds. Sorry, I don't know where the 6 came from. With a mean of 30.7 pounds and a standard deviation of 3.6 pounds. Which means I can write it in this way. Remember that if they say, if we're given this information, what they're telling us is, number one, that it's normal, or approximately normal. They're telling us that this is the mean, and this is the standard deviation, right? So you're able to get just this information, and it's assumed that all of these things are true. That the distribution is approximately normal, that the mean is 30.7, and that the standard deviation is 3.6. From that, I can answer the question, what is the probability that a randomly selected 3-year-old female weighs at least 30 pounds, okay? So, what is the probability that a randomly selected female selected female weighs at least 30 pounds? All right, so just as we did before, we're going to draw a picture of what that looks like in terms of a normal distribution, right? So I draw my picture. Sorry. So my mean is 30.7. And so 30 pounds is going to be slightly below. At least means what? Which side do I shade? Yeah. Right? Which means that, yeah, okay, cool. We're good. Okay, you guys remember how to do that? It's been a while. Remember we had this z-score, which was x minus over sigma. Right? Okay. Well, let's go ahead and add the notation, right? So we're going to go ahead and calculate this. It's 30 minus 30.7 over, what was this, 3.7? 3.6. I'm having a hard time keeping these 6 and 7s in my mind. This turns out to be, give me a z-score of negative 0.19. All right, so now we add the notation. What we want to know is the probability that z is greater than or equal to. Oh my God. We don't care about this. We're looking for the probability that z is greater than or equal to negative. All right, so in order to find this, we need to find an entry for negative 0.19, right? And then we can take the complement. There are actually a bunch of different ways we can do that, right? We could also look at the other side since they're proportional, right? We could look at the entry on the table for positive 0.19, and that would be the same as well. Let's go ahead and find, so from the table, we will get, and let's look at our table, at negative 0.19, so negative 0.19, that's our entry on our table, right? Cool, so 0.4247. But this gives us the area to the right. To the left, I'm sorry. I got backwards. Right, this gives us the area to the left. So in order to find the area to the right, we have to use the complement rule. So we use 1 minus 0.4247, which is all right, so we're going to put that into if we were to put that into context, we would say that the probability that a randomly selected female weighs at least 30 pounds would be approximately 0.575, right? Or you could say approximately 58%. Cool. All right. And that's it. And there will be many more examples like that. So you're going to have to recall using the normal distribution. The thing that we're going to add is this piece, right? A little notation. We're talking about it in terms of probability. All right, that is 6.1 in a nutshell.